Hello everyone, welcome back to ECE410 Power Electronics, class number 7. In this class, we're gonna use power filtering and energy balance to design a converter. All right, so let's get started here. For like when you do power filtering, you try to get unwanted frequency out of your way, so you only deal with wanted frequency for the load. So there are few way of doing it. One of the way of doing it is the resonant circuit. When a resonance happen, your basically inductive part of the circuit and the capacitive part of the circuit becomes equal to each other. So let's say this is the resonance circuit right here. So this one is your inductive and capacitive part of it. At the resonant frequency, what will happen, your inductive impedance should be equal to your capacitive impedance. And as you know that your inductive impedance is omega L, and your capacitive, I'm only talking about magnitude here, and your capacitive impedance would be 1 over omega C. So from there, if you modify that equation, that will become omega wanted frequency will be 1 over L C square root. So that means that this case where at the resonant frequency, this will these two will not affect the circuit. This one and this one will not affect the circuit at resonant frequency. So your load see the resonant frequency coming across the load. So square wave at the desired frequency is delivered to the resonant load. The resistor load only see the fundamental of the sinusoidal frequency. So we can you can design the L and C such way that at the fundamental frequency the impedance are equal to each other. Then your load only see the fundamental frequency. Other frequency should be blocked by the L and C circuit. And let's use energy balance. Also, your filter equations for L and C to design the converter. For this converter over here, we're using 200 kilohertz. So 200 kilohertz is a switching frequency, and your T, the period is 1 over F. If I use this equation, your T should be here is 5 microseconds, right? And you have the inductor with 1 millihenry, capacitor 10 microfarad, and your R is 10 ohms, and input voltage is 5 volts. So let's see, can we see what kind of your ripples you can have in this circuit, current ripples and also the voltage ripples. All right. So this is the circuit over here. If you the voltage across this one is VL, voltage across this one is VC, right? And current going to the inductor is IL. So inductor between the switching, inductor is large enough to have the inductor current constant, and also capacitor is large enough to have the output voltage constant. That's the goal for these two elements over here. When switch 1 is on, 2 is off here. So 1 is on, 2 is off, 1 on here, right? Then this is the circuit here. So in this circuit over here, your inductor is getting the energy from the source, and your capacitor is supplying the voltage to the output. So when switch 1 is on, two things happening. Inductor is charging, capacitor is discharging. And on the other side, when switch 2 is on, 1 is off, so it's 2 on here, right? Then what's happening here, your inductor is discharging and capacitor is charging. So opposite state, 1 is on, capacitor is discharging, inductor is charging. 2 is on, inductor is discharging, capacitor is charging. So switch 1 is on, the input energy to the inductor. So remember that is on for 3/4 of the period. So our D ratio here is 3/4. So switch 1 is on for 3/4 of the period. So as I said, when one is on, inductor is getting energy from the source. So that would be VL voltage, IL, right? And your time is on because you have make the energy here, so it should be 3/4T, right? That's the energy coming into the inductor. And which 2 is on, the input is now when switch 2 is on. So now what will happen, your inductor is gonna discharge. So that would be VL, again VL IL T over 4 here. So this 2VL has different explanation. Let me explain here. When switch 1 is on, if I go back to the next one, when switch 1 is on, there's a VL over here, V in. So VL is basically equal to V in, right? When switch 2 is on, your VL over here is, if you use the KVL from here all the way out here, you'll see that your VL is V in minus V out, right? So over here then, this VL over here, this one would be replaced by V in, and this one would be replaced, let me do it here, it would be V in minus V out times IL times T over 4, right? And this one will become over here is V in IL 3 over 4 T, right? So again, if we add this to the for two switching cycle, if we add this on and off switch, this should be 0. If we do that, if we make it 0, then if we equate them, so if we, what I'm talking about here, if we say V in IL 3 over 4 T plus V in minus V out, right? IL T over 4 should be equal to 0, right? If we do that, your V out becomes 4 V in, and V in is 5 volts. So then your V out basically 20 volts, right? So your V out is 20 volt, V in is 5 volts. So now you're maintaining 20 volts out there, and you have a, if you go back here, you have a 10 ohm resistor, right? So if you now come here, so you have 10 ohm resistors, you have 20 volts, you have 2 amps current, right? You have 2 amps current going in the output, is load current, so your power is 40 watt. Now we're assuming the lossless converter, that means your input power also 40, so your input power also 40 watt, right? That means your input voltage here times input current will give you that. If you solve it, you're going to get that 8 amps is input current. That current also your inductor current. If you look at here, input current is basically your inductor current, right? So average inductor current, average input current, the same thing for this particular circuit. All right. So that is your input current, and so let's see how it looks like. So now if you look at now what happening here, remember that the VL is equal to V in here, which is 5 volts, right? So this is your V in, which is 5 volts. And then when your switch 1 is on, which is the 3/4 of the period, and for this period over here, your VL is V in minus V out, right? Which is 5 volts minus 20 volts is negative 15 volts. Look at here, negative 15 volts. So when switch 1 is on, your inductor voltage is 5 volts. When switch 2 is on, 1 is off, inductor voltage is negative 15 volts. So now if we average them, here, so let's say 5 volts, which switch 1 is on, 5 volts, right? How long is on? 3/4, right? And plus negative 15 volts times 1/4. If you now do the math, that should be 0. That means average voltage across the inductor over the period is 0. So that means inductor does not store any energy over a period. That's how you conserved energy loss in there. The energy law actually dictates that inductor cannot store energy over a period. So now, if you now go back here, so you know that this input voltage is 5 volts, inductor sees 5 volts when switch is on. How many times is 3.75 microsecond, which is basically 3/4 of T. T is your 5 microseconds, right? T is your 5 microsecond, right? So then when switch 1 is off, 2 is on, inductor C, negative 15 volts for how long? That is 1/4 of T. So T is, this is 1/4 of T. T is 5 microseconds, right? So now, you know that induced voltage inductor, you all know that here is VL equals to 5, VL equals to L di dt. When your di is very small, we can replace di dt with delta I, delta t, right? So now, over here, I know the value of L. I know the delta T, when switch 1 is on, is 3.75 1.75 microseconds, right? So then I can easily find delta I, right? I can easily find delta I. So what is delta I? Is the current ripple in the inductor current. So now if I do the math over here, so is 5 volts, right? 3.75 microsecond divided by 1 millihenry, that will give you 0.0188 amps. So that's the peak-to-peak ripple in inductor current. How does it look like? Let's say your inductor current, the inductor is 8 amps, right? So this is the 8 amps inductor current, which is your average inductor current. So now you have a period here, right? So for this period over here, I'm going to draw only one here. So for this over here, inductor current goes up, all right? Then for this period is comes down here. So like that. So this is this ripple over here is 0.0188 amps, and it's continue from there. Then it is continue from there. So that means 0.0188 amps is basically 25% of your of IL, which is average current 8 amps. And you can check it, the same answer for the period when switch 1 is off, 2 is on, when inductor discharging, and you know that period your VL is negative 15 volts, right? And your delta T is 1.75 microseconds, right? If I use it now, so VL is L di dt, right? So it's negative 15 volts here. L is 1 millihenry, right? And this is negative because it is now decreasing. Look at that here. It's decreasing. So your slope is now negative now. So delta I over 1.75 microsecond. Now, if you do the math here, we'll also see that is the same answer, because this is always same value, 0.0188 amps, which is the ripple, peak-to-peak ripple of the inductor current. All right. So that's how you see how much current ripple you have in the inductor current. And this is picks again here, what I said, this same thing over here. So you can see that what's happening into the inductor current. So average value of 8 amps, then you have a ripple of 0.0188. Now, if you do the same thing for the capacitor, you have to see here, capacitor has a current IC here. This is the IC current, this is the I load, right? So when switch 1 is on, 2 is off, your IC is equal to actually negative I load, right? Let me do it over here. So let's say when switch, this one is on, right, this one is off, then your IL current over here, your IL current come in here. So at this node, if I take IL, right, equal to incoming current and outgoing current is IC and also I load, right, and equal to 0, and this is the 8 amps, right? This is IC, I don't know yet, and this is your 2 amps equal to 0. Then your IC negative just 6 amps, right? So when switch 2 is on, your IC is 6 amps. Now when switch 1 is on, I'm going to take it off here. When switch 1 is on here, so this one is off. The only current here is node has 2 current now. So that for this combination over here, I have IC is going out, and also I load is going out. Both are going out, so both are negative, should be equal to 0. Then your IC is negative I load. So that means load is 2 amps, as you know from the previous calculation. So IC is negative 2 amps. So switch 1 is on, 2 is off, IC is negative 2 amps. Switch 1 is off, 2 is on, IC is 6 amps. So you can use either of them to the calculation for capacitor voltage ripple. So let's do one here. So let's do the one that when switch 2 is on is 6 amp and 125 microsecond is on. And let's use this one for the first time calculation over here. Let's see what happens. So now you see, let's do it here. Let's do it from the beginning. So your IC is C dV over dt. I can do it over here in delta. So is delta V, which is ripple, peak-to-peak ripple, delta T, right? So over here, if I use in the 6 amps one is 6 amps, and your C is 10 microfarad. I don't know delta V, but I know this one is 1.7, so 1.25 microsecond, right? If I use the math here, delta V should be a very small value here. Let me see what the calculation says. Is 0.75 volts, right? So that is one I'm using this one. You should get the same answer when you use this one. If you try that, it will be same equation, IC, C delta V, delta T, right? Your delta T is 3.75, slope is negative, IC is negative 2 amps, and C, you know this, so delta V over here should also get 0.75 volts. You should check it. You should check it. All right. So now, this is the calculation for both current and for both switch turn on and off. So now, here's my question for you. So if I don't have the capacitor in the circuit for this particular converter, what will happen? Think about it. If I don't have the inductor in the circuit, what will happen? And if I don't have the resistor in the circuit, what will happen? I want to make you think that what will happen if we don't have one of these components. So we can discuss that in the class when I come back to the class. So think about it, what will happen if we don't have a inductor or a capacitor or a resistor in the circuit. Then you'll see why they need to be there for a complete circuit design, right? So with that, I think I did the example. There are three of them. There are actually three different examples here. Practice problem that we can solve together in the class. So we're gonna use the same concept to solve this in the class, and I'll see you in the class. Please come back, watch the video, and take notes. Then it will make your learning a lot easier in class. Thank you.